In this elementary algebra review tape, we're going to be going over our work on exponents. You'll remember that a to the nth power, where n is a positive integer or natural number, means a times itself n times. In other words, n factors of a. Here we're assuming that n is a positive integer or a natural number. For example, a to the third power, a times a times a. Okay, in our lessons on exponents, we also extended the idea of exponents to account for zero exponents and negative integer exponents. And we defined them in the following way. A to the 0 power was defined to be 1 so long as a was not 0. And a to, say, the minus n power, where n is a positive integer, so this is a to a negative integer power, is defined to be 1 over a to the n. Once again, in both of these, a is assumed to be non-zero. So, for example, if I had a to the minus 4 power, I could write that as 1 over a to the 4th power. With these definitions, the rules that we had for working with exponents, for working with positive integer exponents, also applied for all integer exponents. For example, a to the m times a to the n, a to the m plus n. You kept the base, you add the powers. And a to the m over a to the n, a to the m minus n. Okay, we had these rules originally for positive integer exponents, and now they hold for all integer exponents. And a to the m to the nth power is a to the m n power. Okay, bearing that in mind, let's try to evaluate some expressions involving exponents. In the first example, we would like to evaluate the following expression: 3 to the 0 power plus 6 to the minus 2 power, take away 2 to the minus 3 power. Three to the 0 power, of course, would be, by definition, 1. A to the 0 is 1. 6 to the minus 2 power can be rewritten as 1 over 6 to the 2nd power. Take away, now 2 to the minus 3 power is rewritten as 1 over 2 to the 3rd power. So we have 1 plus 1 over 36 minus 1 over 8. And we have a problem involving addition and subtraction of fractions. Of course, we would like to build fractions equivalent to each of these having the same denominator. We need the lowest common denominator. In this case, if you happen to see it at 72, fine. If not, you could, of course, factor each denominator completely. 36, which is 4 times 9, is 2 times 2 times 3 times 3. And 8, of course, is 2 cubed. So 2 times 2 times 2. So the LCD, 1 is just 1. We take each factor the largest number of times it appears in any one denominator. We have 2 2's here and 3 2's here, so we'll need 2 taken 3 times. 2 3's and no 3's, so we'll need 3 taken twice. And we have 2 times 2 times 2, 8 times 9, 72 is our LCD. So we want to combine over this denominator 72. In each case, build a fraction equivalent to the original one. Here, we multiply the denominator by 72, the numerator as well. Here we multiply the denominator by 2, so we multiply the numerator by 2 as well. Here the denominator is multiplied by 9, so the numerator is also giving us, now combining numerator, 72 plus 2, that's 74, minus 9, or 65 over 72 for our answer in this example. In the second example, we would like to simplify the following. 2 plus 3 to the minus 2 power, all raised to the minus 1 power. Okay, the important thing here is to realize that you cannot do this in the following way. You cannot say it's 2 to the minus 1 and then 3 to the minus 2 times minus 1, or 3 squared. This cannot be done. You cannot distribute the power in general in this fashion. If you have a plus b to the m, it is not a to the m plus b to the n. It is true that we had a rule that a times b to the m, when these are joined by multiplication, this is a to the m times b to the m. But when they're joined by addition or subtraction, you cannot just distribute the power. And to see that, you could, of course, look at, for example, a plus b squared. This is not just a squared plus b squared. It's, of course, a plus b times a plus b, or a squared plus 2ab plus b squared. Whereas ab squared, this is a squared times b squared. So when we have terms here rather than factors that are joined by multiplication, you cannot distribute the powers. So in that case, the only thing that we can do is to work from the inside of the parentheses out. Simplify within the parentheses, and at the end, take it to the minus 1 power. Okay, so let's try to do this now the proper way. Inside the parentheses, we can write this as 2 plus, now 3 to the minus 2 is 1 over 3 squared. And all of this can be taken to the minus 1 power. This is 2 plus 1/9 to the minus 1 power. Now, 2 plus 1/9, 2 can be thought of as 18/9 plus 1/9, giving us 19/9 to the minus 1 power. Now, you could think of this as something to the minus 1 power, so it's 1 over 19/9 to the first power, using the idea that a to the minus n is 1 over a to the n. 19/9 to the minus 1 power is 1 over 19/9 to the first power. And instead of dividing by the fraction 19/9, it's permitted to invert and multiply by 9/19, giving us a final answer of 9/19. There is a more direct route. It is perfectly okay to go from here to the end by realizing that this minus 1 power, okay, indicates that the reciprocal is to be taken. Okay, you can see, I mean, it's easy to show in general. It works this way. You have a fraction to the minus 1 power. It's 1 over that fraction to the first power, but dividing by that fraction, you can invert and multiply, so you just get the reciprocal. So if you want to, you can do it this way or directly. The minus 1 power indicates the reciprocal. As our third example, let's simplify the following expression. X cubed times x to the fifth times x to the minus 2 power. Now, we've had work on this involving positive integer exponents. When the negative exponents are in there, same procedure. We keep the common base and we combine the powers. We add powers, and here we're going to subtract. So 3 plus 5 minus 2, giving us x to the 8 minus 2, or x to the 6th power. X to the a times x to the b is x to the a plus b. That's x to the 8th. And then x to the 8th times x to the minus 2, 8 and minus 2 giving you 6. It's the same rule. The rules work for positive or negative integer exponents. In our fourth example, we have x to the 7th divided by x to the minus 4. X to the a over x to the b is x to the a minus b power. Okay, whether the powers are positive, negative integers, it doesn't matter. The same procedure, giving us x to the 11th power here. In our next example, we want to simplify this. X cubed y to the minus 4 power over x to the minus 2 times y to the minus 3 power. Okay, what we can do here is sort of break this into two smaller problems. You can think of it as x to the 3 over x to the minus 2, group the x's together, times y to the minus 4 over y to the minus 3. And work them separately and multiply the results. So here, x to the a over x to the b is x to the a minus b. And here, the same thing, y to the a over y to the b is y to the a minus b. Minus 4 minus a minus 3. This gives us x to the 3 minus a minus 2, or 3 plus 2, or x to the 5th. Y to, let's see, minus 4 minus a minus 3 is minus 4 plus 3. Minus 4 plus 3 is minus 1. And we generally like to give our answers in problems involving exponents only so that they're only involving positive exponents. Okay, so we would rewrite this as x to the 5th over y. Okay, so simplifying in an exponent problem generally means to get the answer so that it only involves positive exponents. At the end, y to the minus 1 could be thought of as 1 over y to the 1. X to the 5th times 1 over y is x to the 5th over y. Okay, let's try a slightly more complicated problem involving exponents. We want to simplify the following and express the answer with positive exponents. And the problem is the following. 2x to the minus 3 y squared, all raised to the 3rd power, over 4 times y to the minus 1, and only the xy to the minus 1 is raised to the minus 5th power. Now, in the numerator, we do have a product here, and you can distribute the power for a product. It's like a, b, c to the mth power. It's a to the m times b to the m times c to the m. So we can make this 2 to the 3rd power, x to the minus 3 raised to the 3rd power, and y squared to the 3rd power, over, now the 4 is not being raised to the minus 5th power. That's by itself. Here, once again, ab to the m power is a to the m times b to the m power. So x to the minus 5 power times y to the minus 1 to the minus 5 power. Let's see what we have here. 2 cubed, that's 8. Here we have x to the minus 3 power cubed is x to the minus 9 power. x to the a to the b is x to the ab. You multiply the powers here. Y squared cubed is y to the 6th power. You are multiplying the powers. And over 4, x to the minus 5, y to the minus 1 to the minus 5 power is y to the plus 5 power. And what we can do here is break this into 3 smaller problems. First take care of the constants and the x's and then the y's. So what do we get? 8 divided by 4 gives us 2. X to the minus 9 over x to the minus 5 is x to the, it's like x to the a over x to the b. It's x to the a minus b. That is, you subtract the powers when you divide. And here, y to the 6 minus 5 power. So this is 2. X to the minus 9 minus a minus 5, minus 9 plus 5 minus 4 power. Y to the 1 power. And finally, to get our answer completely in terms of positive exponents, x to the minus 4 can be rewritten as 1 over x to the 4th, giving us 2y over x to the 4th as our final answer. In the following example, I would like to work out a problem which will eventually involve exponents. Right now, it just looks like a numerical example. It's a problem from arithmetic. 24,000 times 0.003 divided by 60 times 0.04. Okay, now, very often, it's easier to do a problem like this if you convert all the numbers to scientific or power of 10 notation. That is, we rewrite each number as, say, a number between 1 and 10 times some power of 10. And we can always do this. And then, using our rules for working with exponents, we can simplify this problem. So we would like to here convert to scientific notation or power of 10 notation and evaluate. Strictly speaking, the scientific notation means a number between 1 and 10 times the power of 10. So we would have to do the following. 24,000 would be rewritten as 2.4, that's a number between 1 and 10, times 10 to the 1, 2, 3, 4th power. It would be 2.4, the decimal would be here, and then you'd have to say times 10 to the 1, 2, 3, 4 to move it 4 places to the right to get 24,000. Then 3.0 times 10 to the, let's see, the decimal were here for 3. We'd have them to move it to the left once, twice, 3 times. So 3.0 times 10 to the minus 3 power. 60 could be thought of as 6.0 times 10 to the 1st power. 6 times 10, of course, is 60. And finally, 0.04 can be thought of as 4 times 10. 4 times 10 to the minus 2 power, because you'd move the decimal 2 places to the left. By the way, this is strict scientific notation. If you want to use a modified scientific notation, for example, to write 24,000 is 24 times 10 cubed. In fact, in this problem, that would work out a little simpler. Okay, so it's okay to do that. The basic idea, though, is to be able to handle large numbers involving, say, positive powers of 10 and small decimals in the same problem very simply. Okay, so if you want to make it 2.4 times 10 to the 4th or 24 times 10 cubed, that's not really important. The important thing is that we don't have to worry about these decimals here. Okay, now what we do is we regroup so that the constants here, the numbers that are not in power, the numbers without the tens, okay, are sort of together, and then we'll put the powers of 10 together. So what do we have? We have 2.4 times 3 over 6 times 4 times 10 to the 4th times 10 to the minus 3 over 10 to the 1 times 10 to the minus 2. Let's see. Well, 3 goes into 6 twice. 4 goes into 2.4. It leaves you with 0.6. And finally, 2 into 0.6 leaves you with 0.3. And then we'll have times something else over here. And this is what I meant by it being a little easier. If we had made it 24 times 10 cubed, we would not have to worry about this decimal over here. We would have had a 3 rather than the 0.3. And it would have been taken care of on the other side. Now, let's look and see what we have here. In the numerator, we have 10 to the 4th times 10 to the minus 3, which is 10 to the 1. You keep when you're multiplying here, you keep the same base, you add the powers. And 10 to the 1 times 10 to the minus 2 is 10 to the minus 1 power. Once again, you are multiplying, you add the powers. And we get 0.3 times 10. Now, when you're dividing, you have to subtract the power. So 1 minus a minus 1, that's the second power. So we get 0.3 times 10 to the second power. And multiplying by 10 to the second power has the effect of moving the decimal 2 places to the right. So from 0.3 to 3 and then to 30, giving us our final answer of 30. And the last problem on this reviewed tape, I want to multiply out x minus 3 cubed. And I brought this up before. You cannot distribute the power. This is not x cubed minus 27. You cannot say x cubed take away 3 cubed. What you have to do is say that x minus 3 cubed is x minus 3 times x minus 3 times x minus 3. Now let's see what we get. We could say it's x minus 3 times, now these two can be multiplied together using FOIL. First, x squared minus 3x minus 3x minus 6x, and then last plus 9. And then by repeated use of distributed law, you'll be able to complete the problem. We can write this as, think of this as like a plus b times c. So it's going to be a times c plus b times c. That is x times x squared minus 6x plus 9 minus 3 times x squared minus 6x plus 9. A plus b times c, a times c plus b times c. Now we will distribute the x through the parentheses here. X cubed minus 6x squared plus 9x. And here we're going to distribute the minus 3 through the parentheses. Minus 3x squared minus 3 times minus 6x for plus 18x. Minus 3 times 9 for minus 27. And finally, combining like terms, well, it's the only term involving x cubed. We have a minus 6x squared and a minus 3x squared for a minus 9x squared. Let's see, the x terms, we have a plus 9x and a plus 18x for plus 27x. And for the constant terms, we just have the minus 27. So here we have x minus 3 quantity cubed. And you see it's a lot more involved than just x cubed minus 27. And this brings us to the end of our tape.